Hello students, in this video I'll continue to the properties of ideals, so that as we discussed in previous lecture, so what is a principal ideal and what do you mean by principal ideal ring there. So in this we start with the properties of that principal ideal ring. The ring of integers is a principal ideal ring. So now let us see the proof of this. The ring of integers say is said that which contains an elements of 0 plus or minus 1 plus or minus 2 and so on plus or minus 3. So now let I be an ideal of Z. Now let us let n be the least positive integer in I, that is n belongs to I, and also let k be an element of I, any element of I there. Now by taking the division algorithm, we can find the integers q and r such that k can be expressed as, that is the nq plus r, where r is the remainder, that is the domain of r is 0 to n there. So now that remainder can be expressed as k minus nq. So since I is an ideal of Z, so for n is an element of I and q is an element of integers set, and nq is also belongs to I, and also k is definitely belongs to I there, because since I is an element of Z, so n definitely it is an element of I there. So then q is an element of Z, so that I into Z, so that definitely it is an element nq is belongs to I there. So that this nq is belongs to I, this k is also belongs to I. Definitely this k minus nq is member of I there, because since I is an ideal, so that this k minus nq is an element of I there. So it is what there, it is R there. So that this remainder is also belongs to I there, where R is running from 0 to n there. But n is the least positive integer in I. Now only the possibility is R equal to 0, because none other than 0, so that the remainder is only 0, because n is the least positive integer in I. So thus this R is 0, so that k equal to nq. This shows that any arbitrary element of k is element of I is a multiple of n there. Hence I is a principal ideal ring, which is generated by n there. So since n is arbitrary, because it is an definitely it holds good for the principal ideal definition, this n is that is this ideal, principal ideal, which is generated by this n only. So that's why this is a what now, since n is arbitrary element, so it is a least element. So every ideal of Z is a principal ideal there. Consequently, this integer set is also a principal ideal ring there. So that is what we have discussed there, because only we have started with that this IB set of integers there. So we choose that is the IB an ideal of Z, and also we choose the least element, we assume that, which is positive integer in I, that is n, and also k be any element of I. So in order to make it put it in the expression of this form, so by using the division algorithm, we can find the integers q and r here. What is the contribution of q and r? Q is quotient and r is remainder, such that k can be expressed as nq plus r, where r is that is running from 0 to n there. So r equal to, that means r is, that is k minus nq. Since I is an ideal of Z, so n is the least positive integer, so that it is the n is also element of I and q is also element of z. So definitely nq is member of that I. So also k is also member of I. That means this k minus nq is member of ideal there, because since I is an ideal, so this k minus nq is R, it is an element. So R is running from 0 to n there. But n is the least positive integer in I, but only the possibility R is, that is 0. Means what? It is only R remainder is 0. Thus k equal to nq. This shows that any arbitrary element k is a member of I is a multiple of n. Hence I is the principal ideal which is generated by n. Since n is arbitrary, so every ideal of Z is the principal ideal. So consequently, Z is a principal ideal ring there, because it is wind up with the principal ideal definition there. That now let us move on to the next theorem. So if 0 ring and R are the only ideals of a commutative ring with unity, then R is a field, or else a field has no proper ideal. Already I have explained in previous videos, so that it's need not to explain once again. So now we can take it to another exercise, that if I is the right ideal and J is the left ideal of R, ring R, and I intersection J is the 0 ring, and then this product of A into B is 0 for all A is in I and B is in J there. So now let us take this, let A is in I and R is in R. So product of A and I are this is because AR is belongs to I, because I is an ideal, right ideal there. So and also let us take B is an element of J and R is in R. So RB is also belongs to J, because J is the left ideal. That's why we can take it. That is B is the member of I there, member of J there. That's why it is in left there. That's why RB there. So because J is the left ideal. So now A is in I. It is a subset of R. That means definitely A is in R and B is in J there. So A is in R and B is in J, so that the product of these two, it is in J, because J is the left ideal. And also B is in J, which is also subset of R. B is in R and A is in I, and again it is the product is in J, because since I is an ideal, left right ideal there. So therefore AB is in I and AB is in J, so that this intersection of I and J, which has the element product of A and B there, it implies AB is member of intersection of I and J there. But given that this intersection is a this intersection is 0 element there, so that intersection common element is 0, so that is non-empty. So that's why we can take it this AB is 0 there. So for all A is in I and B is in J there. So that is what we are discussing. And another question here, if I is an ideal of a ring R, then CI, that is CI is a subring of, CI means what? Center of a ring I there. So that CI is can be defined as this R is in I and this AR minus RA, that is in I for all A is in R, is a subring of R there. Means what? Suppose if I is an ideal of a ring R, then this center of a ring this is a subring of R there, because since it can be defined as these two ideals, it is a closure under addition property satisfied. So definitely it is a subring of R there. Now in order to prove that, so let us take R1 and R2 is an element of CI. That means AR1 minus, because R1 minus R1A is member phi, and R2 minus R2A is also member phi there. So we need to prove the first condition of subring. So A into R1 minus R2 minus R1 minus R2, because we are having the defined that Ci like this only. That's why we can take it there, and then we can club the terms like this. So again, make you should be the form like this here. AR and RA we have defined in Ci. So it is given, since it is given like this, since AR1 minus R1A is in I, and AR2 minus R2A is also member of I there, because both are in there, so that definitely also I is an ideal. So R1 minus R2 R1A minus R2 minus R2A is member of I there. So it has satisfied the closure under addition this I there. So definitely this expression is also A into R1 minus R2 minus R1 minus R2 into A is, is member of I there. So then this expression, because this expression is in Ci as defined in given there, so that means R1 minus R2 is member of Ci, so that this Ci is a satisfied closure under addition property there. And now again that A R1 into R2 minus, because we need to product, we can show that here. So that A R1 into R2 minus R1 into R2A there. So that again we need to show that commutative properties also satisfied under multiplication there. Since I is an ideal of R, so AR1 comma AR2A is also member of I there. Therefore, AR1 into R2 comma R1 into R2A is also member, because I is an ideal. So this again, it is the commutative property holds that, because just we are rewriting and clubbing like this, the terms looks like as we have defined in Ci. So it is put it like this. So then as A into R1 R2 minus R1 into R2A is member of I, because since I is an ideal there, so then product of this R1 into R2 is also there. So this I is also satisfied the commutative property under multiplication, so that Ci is a subring of R there. So next time I will explain the next questions and properties of ideals there. Thank you.